Okay guys, Caleb Matthew. Wow, what a class period today. It's about 11:05, so you guys have been gone about 25 minutes. We'll see if we can't get this video up and running here. Good job today. I will give you guys credit. You have really been troopers when it comes to this 2-hour class on Monday, so good job. And I love this stuff, and my mind is still fried right now. So we did a lot of math, so good job. Way to hang in there. Let's see if we can't do some more. Okay, let's wipe this out as quickly as possible. Okay, number 60 on page 143, that's right where we left off. We're looking at the difference quotient, and again that formula is f of x plus h minus f of x. And I'm not really going to worry about all over h until the very end of the problem. So let's start off with f of x plus h. That means everywhere in this function I've got to put x plus h. So x plus h over 2 minus x plus h, and then minus the entire fraction. In fact, I'm not going to put parentheses because we know it's minus the entire fraction, 2 minus x. Now all of this would be over h, but we're not going to worry about that right now. We have a truckload of work to do on this problem, okay? So don't be scared of that. Just be ready for it. First of all, we're going to have to simplify this denominator. Take this negative sign and multiply it through. So 2 negative x negative h. Now, unfortunately, men, a common denominator for these two fractions would be 2 minus x minus h times 2 minus x. So we're going to have to write that a couple of times. So there's our common denominator with a minus sign here. Now, what do we have extra here that we don't have here? 2 minus x. So we have x plus h times 2 minus x. Now, what do we have in this denominator we don't have here? Well, we have 2 minus x minus h, and then bring down your x times x. So as you can see, unfortunately, we have a ton of simplifying to do, okay? So first of all, in this fraction right here, and your old teacher messed up, sorry, I apologize. There we go. In your first fraction here, x plus h times 2 minus x, you should get 2x minus x squared plus 2h minus xh, okay? And then in this fraction over here, we should have 2x minus x squared minus xh, okay? Now we're going to have to go ahead and add another page like I told you we're going to have to. Now what I did right there is I simplified this numerator and I simplified this numerator into this down here. I hope I've not made a little mistake somewhere, if so that's going to be really frustrating later, but I think we're doing okay. Alright, now we can go ahead and we can put these two fractions together. Now don't forget you're subtracting this entire numerator, so what you really have is 2x minus x squared plus 2h minus xh minus 2x plus x squared plus xh all over your common denominator, okay? Now notice all of these signs up here changed because of this negative sign right here. Now let's cross off. I've got a 2x and a negative 2x. I've got a negative x squared and a positive x squared, a negative xh and a positive xh. So here's what I finally have. I finally have 2h over this common denominator right here. And then don't forget, that's all over what? H. So really what I have is this fraction right here divided by h. So that's what I'm going to do. I'm going to put divided by h over 1. Now, of course, if I'm taking a fraction divided by a fraction, I would flip this second fraction right here, and then I would multiply. And then notice I have one term here and one term here, so I can definitely do some cross canceling. So I have an h that will cancel with an h, and so 2 times 1 is 2. And then this whole denominator times 1 is just going to be this whole denominator right here. And if you wanted to simplify the denominator and multiply it out, you could. But that is the answer, okay? All right, moving on. I hope that helps. Okay, let's do f of g of x and g of f of x. So first of all, let's start off with f of g of x. Here we go. F of g of x. The first letter on the outside is f, so we take our f function, x plus 3, and everywhere there's an x, we put a parenthesis. And then my next number on the inside, or my next letter is g, so I pick up g and I put it on the inside, x minus 3. So I'm left with x minus 3 plus 3, which is just x. Very good. Now let's do g of f of x. Notice how I wrote it in two different notations so you get used to that. Okay, my first letter is g, so I take my g function, x minus 3, and everywhere there's an x, I put a parenthesis. And then my next letter is f, so I pick up my f function and I put it inside the parentheses. And now I have x plus 3 minus 3, which is just x. That won't happen all the time. That's a coincidence, okay? All right, moving on to number 76. Let's start off with f of g of x. Okay, my first letter is f, and so I take my f function right here, 6 over x, and I put a parenthesis where the x is. My next letter is g, so where the parentheses is, I put my g function right here, and that would be 1 over 2x plus 1. So here's what I have. This is not bad. I have 6 divided by 1 over 2x minus 1. So really put the 6 over 1, and then we're simply going to take this fraction here and flip it. And then multiply. Not too bad. So 1 times 1, of course, is 1, and then 6 times 2x minus 1 would be 12x minus 6. 6 times 2x, 6 times negative 1. And it's over 1, so really your answer is 12 minus x. That's not bad. That's f of g of x. Now let's take a look at g of f of x, okay? And again, I'm using a different notation, so you're used to that. Okay, g of f of x, so my outside letter is a g. So I take my g function, everywhere there's an x, I'm going to put a parenthesis. There we go. Here's my x, and I put a parenthesis right there. Now, the next letter is f, so I'm going to put 6 over x right here. And now let's do some simplifying. First of all, I have 2 times 6 over x, or 2 over 1 times 6 over x. So if I took 2 times 6, that would be 12. 1 times x is x, plus 1. So I have 12 over x plus 1. Now think about it, guys. This is really easy to get a quick common denominator. Your denominator here is x, and here you have a 1. So how can I write 1 so that it has a denominator of x? Oh my goodness, guys, just think about that. X over x. I mean, anything over itself is 1, right? So there we go. So x over x is 1. Now I have a common denominator. So I have 1 over 12 plus x all over x, right? 12 plus x all over x. So now I have my top, which is a 1 divided by 12 plus x over x. Okay? So that simply means I'm just going to take my numerator right here, move it down here, take my denominator, put it here, and Now we're going to multiply. And of course, 1 times anything is just itself. So 1 over 1 times x over 12 plus x is x over 12 plus x. There, we did it. G of f of x. All right, let's do, I think it's the last one. Let's do one more of these. F of g of x, f of g of x. Your outside letter's f, so you take your x function, and everywhere there's an x, you put a parentheses. Then your next letter is g, so pick up g and put it right here. And you're going to see this is really, really easy. There we go. Well, if you take a fifth root and raise it to the fifth power, you get just what's on the inside. So we're left with x plus 2 minus 2, which is x. Now, let's go ahead and find g of f of x. Take your g function, and everywhere there's an x, we're going to put a parentheses. So here's an x, here's my parentheses, and then your next letter is f, so you pick up your f and you put it on the inside, x to the fifth minus 2. Now let's simplify under the radical here real quick. Under the fifth root, I have x squared minus 2 plus 2. Or not x squared, x to the fifth minus 2 plus 2. That's just going to be x to the fifth. I mean, x to the fifth minus 2 plus 2 is x to the fifth. Well, the fifth root of x to the fifth is just x. Again, that's a coincidence that will not always happen. Okay, so there we go. Let me get a drink here real quick, guys. And that's composition of functions, okay? Composition of functions. And we did have one more. I apologize. I did not realize that. X plus 2 over x. Okay, we'll go really fast. F of g of x. F of g of x. Well, you take your f function, and everywhere there's an x, you put a parentheses. And then in this parentheses, I'm going to put g, which is x plus 2 over x. There we go. This is not as bad as it looks. How do you write 2 so that it has a denominator of x? Well, think about it, guys. It's not that bad. If I put 2x over x, doesn't that reduce back down to 2? Sure it does. So 2x over x is the same thing as 2. Now I've got a common denominator, so I have x plus 2 minus 2x. So I have 1 over x plus 2 minus 2x all over x. X plus 2 minus 2x. Now, I can simplify x plus 2 minus 2x, this expression right here that I've circled. Now I would have 1 over minus x plus 2 all over x, because a positive x and a negative 2x is a negative 1x plus 2. And now you should know what to do. I mean, you have up top here you have a 1, so that's 1 over 1 divided by this fraction here. Well, let's just go ahead and flip it and multiply. So I have x over negative x plus 2. And 1 times anything, 1 over 1 times anything is just itself. So we get this right here for an answer. There we go. Totally sufficient. Totally fine. Okay. All right. Moving on to g of f of x real quick. G of f of x. All right. Well, we take our g function right here. Everywhere there's an x, we're going to put a parenthesis. So parentheses plus 2 all over parentheses. And then the next letter here is f. So in this parentheses, I'm going to put 1 over x minus 2. And right here, I'll put 1 over x minus 2. Now, again, it's not that hard. It's really not that hard, students. I mean, you want to add these two fractions together right here, 1 over x minus 2, and of course your 2 is over 1. It's really not that hard to find a common denominator when it's just a whole number like this. I mean, look, just put 2 times x minus 2 over x minus 2. And look, if you were to reduce this fraction, these would cross off, and you're left with 2. So this fraction right here is still the same thing as 2, and I have a common denominator. So I have 1 plus, now watch carefully please, I'm going to go to the right here, this fraction plus this fraction, 1 plus, well I have 2x minus 4. 2 times x is 2x. 2 times negative 2 is negative 4. So I have 1 plus 2x minus 4. 1 plus 2x minus 4 all over 1 over x minus 2. Now, of course, this can be simplified here. 1 plus 2x minus 4 would be the same thing as 2x minus 3 because you have a positive 1 and a negative 4. So let's look at what we really have here. We really have 2x minus 3. All of that can be looked at as over 1, right? Divided by, so here's 2x minus 3 over 1 divided by this fraction here. Well, instead of dividing, let's go ahead and make it multiplying, and let's go ahead and flip this fraction, x minus 2 over 1. So we're finished. I mean, if you were to take 1 times 1 and put a 1 in the denominator, that's fine, but we have this whole top here times this whole top here, and you would get this. You would get 2x squared, let's see, minus 3 minus 4, so minus 7x plus 6 all over 1. There you go. That's it. We did it. So not too bad. Okay. All right. Let me get a drink here. We'll continue on. Moving on to page 163. On 163, numbers 1, 3, and 4, they want us to state whether the graph is symmetric to the x-axis, the y-axis, and also maybe the origin. So let's see. If I were to fold this on the x-axis, would the graph fall right on top of each other? No, it would not. So x-axis symmetry, no good. If I were to fold this graph right on the y-axis, would this graph here fall right on top of this one? Yes, it would. So we definitely have x-axis symmetry, check. And now the origin part. The origin is a little more difficult. Let me give you one. There's two ways to do this, guys. You could first of all fold the graph up and then over, okay, and see if the graph falls on top of each other. Another way I kind of like doing is picking a point like this, and even though we don't know what the values are, we know it's a positive x and a positive y. And then anytime you have origin symmetry, any point that exists over here, the exact opposite of that point will exist over here. So if you were to, let's just say you're over, let's just pretend it's 1, 2, 3, 4, and up 3. So you have positive 4, positive 3. Well, that means over here, negative 4, negative 3 should exist. And it doesn't, does it? I mean, not at all. Not even slightly. And so we do not have origin symmetry. Okay, if we did, there would be a point here on the graph, negative 4, negative 3. Okay, let's take a look at number 3. That's probably the best way to do origin symmetry. Okay, first of all, if you were to fold this graph right on the x-axis, would the graph fall right on top of each other? Yes, it would. So we definitely have x-axis symmetry. Now, if we were to fold this graph like it was a piece of paper right on the y-axis, would this little graph here fall right on top of the other graph over here perfectly? In other words, is it a mirror image? The answer is no. So we do not have y-axis symmetry. We do have x-axis symmetry. Now let's go ahead and test our origin like this. We'll just pretend this point is over about 4 and down about 4. So we have negative 4, negative 4. Now if we have true origin symmetry and right here we have negative 4, negative 4, then that means also over here we should have had a point that exists on the graph that's positive 4, positive 4, and we don't. So we do not have origin symmetry. Now let's take a look at number 4. If you were to fold this graph right on the x-axis, would this part of the graph here fall right on top of this? No, it would not. If you were to fold this graph right here on the y-axis, would this part of the graph here fall right on top of this? No, it would not. And then in reference to origin symmetry, let's just give this point a name like 1, 2, 3, 4, 5, 1, 2, 3, 4. So we're going to say 5, negative 4. Now if you change the signs of both of those, you would have negative 5, positive 4. And by the way, if it's close enough, we're going to assume they meant origin symmetry. And yes, look at that. We have an ordered pair that falls on the graph. That's the exact opposite of this. 5, -4, -5, +4. So yes, we do have origin symmetry. Okay, we do. Okay, moving on now to numbers 16, 20, and 22. And I think that's it for that section. Yeah, 16, 20, and 22. I want you to tell me whether or not we have x-axis, y-axis, or origin symmetry, okay? So let's take a look at that real quick. Okay, let's start off by checking for x-axis symmetry. Everywhere there's a y, we put a -y. And then we simplify and see if we get out the original equation. Well, 7 times -y is -7y. And no, we did not get out the exact original equation. So we do not have x-axis symmetry. Now we're going to check for y-axis symmetry. That means everywhere there's an x, you put a -x. 6 times -x is -6x. Did we get out the original problem that we started with right up here? Exactly. No, we did not. So we know we don't have y-axis or x-axis symmetry. Now to check for origin symmetry, everywhere there's an x, you put a -x. Everywhere there's a y, +7, you put a -y. And then we simplify. 6 times -x is -6x. 7 times -y is -7y equals 0. And it looks like it's not quite the same, but hold it. 0 is neither positive or negative. Now think about this. If I took this one step further and multiplied the entire equation by -1, or in other words, if I went through and just changed all of the signs, this would become a +6x, which you're allowed to do. You can take an equation and go through and change the sign of one term as long as you change the signs of all the terms. So if you went through and changed all the signs, you would get this right here, which matches this perfectly. So yes, number 16 has origin symmetry. All right, number 20. Let's start off by checking for x-axis symmetry. Everywhere there's a y, I'm going to put a -y. And let's see what happens. Okay, -y times -y times -y is -y cubed. And then, just to get y cubed by itself like it is up here, I'm going to go through and change all the signs of each term. This term is negative, so I'm going to make it positive. This term here is positive, so I'm going to make it negative. And did I come up with the original equation? No, I did not, so I do not have x-axis symmetry. Now let's check for y-axis symmetry. Everywhere there's an x, I'm going to put a -x. Now this was pretty easy. Think about it, guys. When you have -x to the second power, -x times -x is x squared times 2 is 2x squared. So yes, you do get out the original problem. So yes, we do have y-axis symmetry. Now we might have origin symmetry too. We got to check for that also, okay? So let's see if we have origin symmetry. Everywhere there's a y, I'm going to put a -y. And everywhere there's an x, I'm going to substitute -x. Alright, -y to the third power is a y cubed, -y cubed, and then -x squared is a +x squared times 2, 2x squared, and then change all of your signs so that y cubed is by itself, and you do not get the original problem. So we do not have origin symmetry. All right, take a look at number 22 real quick and we'll be just about finished with this part here, of course, and then we'll have about 6 or 7 problems left. All right, here we go. Everywhere, let's check for x-axis symmetry. Everywhere there's a y, I'm going to substitute a -y. -y squared is y squared times 2 is 2y squared. So it does come out to the exact problem, so that's good. Now let's check for y-axis symmetry. So everywhere there's an x, I'm going to substitute a -x. Well, A negative x times a negative x is a positive x squared times 5. So 5x squared plus 12. So yes, I get out the original problem. So yes, we have y-axis symmetry. And then origin symmetry is going to be yes also. Everywhere there's a y, I'm going to put a negative y. Everywhere there's an x, I'm going to substitute a negative x. Negative y times negative y is positive y squared, so 2y squared. Negative x times negative x is positive x squared, so 5x squared plus 12. There we go. So this graph here has all three. It has y-axis symmetry, x-axis symmetry, and also origin symmetry. Okay, let me get a drink here and we'll continue on. Number 28. Okay, for number 28, they want us to tell the ordered pair that would exist if the graph has x-axis symmetry, y-axis symmetry, and origin symmetry. Okay, now this point, if we had this point that existed on a graph and we had x-axis symmetry, that means the other point that existed would be this right here. You always change the sign of the y value. Now I know really you don't put a -0. I'm just doing that for kind of theatrical reasons, okay? But you do get the point. Whenever you have x-axis symmetry, that means points exist all over the graph in which the x's stay the same and the y's are opposite. Now for y-axis symmetry, it's just the opposite. If this point existed on a y-axis symmetry graph, then this point here would also exist. You have to change the sign of the x value. So for y-axis symmetry, the x values change on the graph. Now if you have origin symmetry, both signs change. So you would have -7/2, -0. Now you don't need to put a -0. I'm just doing that to prove a point, okay? So if you truly have origin symmetry and this point existed on the graph, this point would have to exist also, okay? Moving on to number 33. 33, 34, and 37 are all just looking at graphs, and we want to know whether it's even, odd, or neither. Now don't forget, even means we have y-axis symmetry. Odd means we have origin symmetry, okay? Well, we definitely have y-axis symmetry. If you were to fold this graph right on the y-axis, this graph right here would fall right on top of this graph. So yes to even. Yes, it's even. Now is it odd also? Well, let's see. Remember how we check origin symmetry? If this point right here existed, positive x, positive y, then that means negative x, negative y would exist down here, and it doesn't. So no, it is not odd. We do not have origin symmetry. Number 34, we definitely have y-axis symmetry. If you were to fold this graph right on the y-axis, this graph right here would fall right on top of this here. So yes, it's definitely even. We have y-axis symmetry. However, is it odd? Well, the answer is going to be no, it is not. This point right here would be a positive x and a negative y. So if this point here existed, then we would have to have a negative x and a positive y up here somewhere that would match this point, a positive x and a negative y, and we don't have that. Or excuse me, I'm sorry, that's incorrect. A negative x and a positive y. Okay? We do not have origin symmetry, thus it is not odd, it is even. All right, number 37. Now, let's take a look. By the way, on number 37, this is the answer here for the one above it, so just ignore that. Okay, now on number 37, first of all, if you were to fold this right on the y-axis, this graph right here would not fall on top of this graph. This graph right here would land right over here. So we know that it's not even because we do not have y-axis symmetry. Maybe it's odd. Well, let's check and see. It looks like it is because this ordered pair here, which is a negative x, positive y, would exist over here, positive x, negative y. but it has to be true for every point. And so notice this point here would be what? It would be 0 comma up y. So then we have to have the point exist that's 0 negative y, and that's this point right here, and it doesn't exist. It's open, and that's why the answer is neither. It's a little tricky. Now if this point would have been closed here, then we would have origin symmetry, because every single point here that exists, its exact opposite point exists over here. This point would be right here. Okay, so you almost have origin symmetry. It's almost odd, but you don't. So this does not have origin symmetry. So this function is neither even nor odd. Okay, 3 problems left. Let's take a look at number 40. Number 40. Okay, we're checking for even or odd for number 40. Well, again, this is pretty redundant. If I'm checking for even, that means what? Y-axis symmetry. So everywhere there's an x, I'm going to substitute negative x. Okay, negative x times negative x times negative x is negative x cubed, times 7 is negative 7x cubed, 4 times negative x is negative 4x minus 2 equals, I'm going to go ahead and make this a y just so it's a little easier, y equals, is this exactly like the problem we started off with? No. So we do not have y-axis symmetry, so it is not even. Now let's try odd. Remember, checking for an odd symmetry means we're checking for symmetry to the symmetry to the origin. And so everywhere there's a y, I'm going to put a negative y, and everywhere there's an x, I'm going to put a negative x. Well, if you simplify the right side, you would get negative 7x cubed minus 4x minus 2, and then go through and change all of the signs so y is by itself. So this term becomes positive, this term becomes positive, this term becomes positive, and this term becomes positive. And look at that. Does this match the original equation exactly? No, it does not. They have a negative 2 here, and we have a positive 2 right there. And that's my cell phone going off. Hold on 1 second, please. Okay, I am back. So we do not have y-axis symmetry, so it's not even. We do not have origin symmetry, so it is not odd. Let's try this one here. All right, let's see what we do. Everywhere, first of all, let's check for y-axis symmetry. So everywhere there's an x, we're going to put a negative x. So all right, and we end up with a negative x is just a negative x plus, now be careful here, 1 over negative x. Okay, you're welcome to pull this, I don't know if you know this or not, but you're welcome to pull a negative sign out from the top or the bottom, but not both, and change this sign here. That's totally legal. So if I have a positive sign here, I can change the sign either in my top or bottom. I'm going to change in the bottom. And if you change the sign in the bottom, then you must change this sign out here also. And so you end up with this right here. Okay? And then that's obviously not at all like the original problem. So we do not have symmetry with respect to the y-axis. Thus, we do not have an even function. Now let's check for odd real quick. Okay? So checking for odd. Everywhere there's a y, I'm going to put a negative y. And everywhere there's an x, I'm going to put a negative x. Bring down your negative y. A negative x is just a negative x. Then like I just showed you over here a second ago, you have 1 over negative x. And you can totally change the sign in the bottom as long as you change the sign here, or you can change the sign in the top as long as you change the sign here. I'm going to go with changing the bottom, so I'm going to make the bottom positive as long as I change the sign out front here. And now, in order to get y by itself, you change the signs of all the terms, so your negative y becomes positive, your x becomes positive, and your fraction becomes positive. And I do have the original problem, so I do have symmetry with respect to the origin, thus I have an odd function. And one more and we're finally done. Here we go. Let's go ahead and make this a y. Alright, let's check for y-axis symmetry for even. Everywhere there is an x, I'm going to substitute negative x. Here we go. Well, if you simplify that, a negative x times a negative x is a positive x squared plus 1. That was a very simple problem, and it definitely matches the original problem. So yes, I do have y-axis symmetry, thus I do have an even function. Now let's see if I have an odd function, okay? Symmetry with respect to the origin. Here's my y. I'm going to put a negative y. And then here's the x. I'll put a negative x. And here we go. Negative y equals, well, when you take negative x times negative x, that's x squared plus 1. And then if you want to get y by itself, you change the sign of your terms. Now watch, the y becomes positive, and students, you do not go inside the radical and do this. Make it a negative x squared and negative 1. That is not correct. What you do is you change the sign outside the radical to a negative radical. And you cannot multiply that negative sign through. That is incorrect to do. Okay, so there we go. That's basically it. Does it match the original problem? It does not. So we do not have origin symmetry, thus we do not have an odd function. However, it was an even function. All right, men, you did well today in class. This has been a little longer than what I wanted, but it is what it is. Call or email if you have any questions. Remember, your tests are due by Wednesday, completely finished.